Hey guys, welcome to another video. So today we continue on with the combinatorics topic where we'll do combinations. In the first video where we did permutations, we tried to cover, set the framework, do a few harder questions, teach you some different techniques. So if you haven't seen that video, please go give it a like. And if you haven't done so, please subscribe to the channel and tell your friends. So combinations, let's get started. Now, I really don't want to give much theory here, but I mean, the difference between combinations and permutations is that combinations has no order, right? That's really important. So for example, if you're selecting 5 players to play on the first team of basketball, it doesn't matter, if you pick Frank first and then Tom, doesn't matter, as long as they're in the team, right? They're part of the first team. So where order doesn't matter, we're talking combinations. So the classic examples are, picking players for a team, selecting members of a committee, and you'll see that in the first question here. But then later on, the harder questions in the combinatorics topic is when sometimes the question sort of blur between combinations and permutations, right? Or combine both. So we'll see some of those as well. Some of the questions that I've also picked today comes from the old 4-unit extension 2 syllabus. So just to basically emphasize the point that this used to be part of the 4-unit syllabus, or at least the harder part. And since that has been removed, a lot of the teachers are throwing those questions or the type of questions that they see in 4-unit into 3-unit. So I just want to cover some of those as well. So let's get started with this first question from Sydney Boys, right? So your classic question where a group of 7 men, 6 women, 5 people are to be selected from a committee. How many committees are? At least 3 men are in the committee. 1 particular man must be on the committee. 1 particular woman is not. And then at the end, 1 particular man, women refuse to be on the committee together. Okay, cool. So subtle differences between 23, but you can see in this question, there is no first question where they go, can you tell me unrestricted total outcomes? They just skipped all that and just went to the good stuff. So let's do it. So part 1, it's cases, right? At least 3 men. So the cases there are, how many men are there? 7, and we're selecting 5. Okay, cool. So you can have a scenario where there's 3 men, 2 women. You can have 4 men, 1 woman, and then of course 5 men committee, right? So to do this, obviously we go and then we sort of add the results from each, right? From 7 men, choose 3, and then from 6 women, choose 2. All right, nothing too hard, but then just be absolutely clear. I always say this to my class, right? So within the same case, we times, and then between the cases, we add, right? So that's like case number. Maybe if I do it more vertical, so it emphasizes the cases being separate, right? So then the next case, 4 men. So from 7, choose 4, and then from the 6 women, choose 1. And then we add that with the last case of 5 men. So from 7, choose all 5. So guys, we have 3 distinct cases. If you plug that on your calculator, right? Hopefully that gives us, I think it's 756. Check that, please. Right, I should be answering them all. 1 particular man is on the committee and 1 particular woman is not on, right? So for the second one, a few restrictions apply. Now, remember, I'm selecting 5 people, right? So if I know that 1 particular man is already in, right? He's selected, right? He's in with a certainty of 1, right? And then all I really need to do, right, for the next part here is to select 4 other people from the remaining people, but I can't select. So I ignore that 1 woman that isn't on the committee, right? So if there's 13 people all up, 1 man selected, 1 of the women are gone, 11 are left, right? So I have 11 people to choose from for my remaining 4, right? So really, mathematically, that's quite simple. So 330 should be your answer. You might want to check that, right? So, and the reason is because this is the man selected and from the 11, woman or one woman removed. Right. Yeah, and we're choosing the 4 remaining. Yeah, not too bad. Now, subtle difference between number 2 and 3. Number 3 says one woman, one man, and one woman refuse to be on together. So this one here, it's like the one above, but sort of both combinations are considered. So you don't just merely double it. The best way, I guess, to do the third case is to basically take the complementary event where they are together. So we take total and we minus the cases where they are together, right? Because you can have a scenario where you can have one man on, the other woman isn't, one woman on, the other man isn't, and then both of them are not on the committee. So to take care of all those situations, you just go total, unrestricted, minus, and when they are together, right? Can't spell together to get her, perfect. Now for total, unrestricted, I've got 13 people and I'm choosing 5, right? That's quite straightforward. Now, if I'm minusing the case where they're both in there together, so the man's in there, the woman's in there, and then I have 11 people to choose my other 3, right? That will give me, hopefully, the situation where that one particular man and woman refuse to be on the committee together, right? Punch in the calculator 1122, I think. Check that, please. So that is, I mean, that's still pretty textbook, right? Because it's a committee question and you just do cases. Hopefully that's okay. I thought I'd begin there because the next few questions are a little bit different, right? Not your usual. So we'll see how we go. Next question. Now, I like this question. It's worth 1 mark, right? For good reason, but some people overcomplicate things, right? A group of 30 students, and this was in the 4-unit paper, right? Group of 30 students divided into 3 groups, 7, 8, 15, right? So I think a lot of people get confused because they're trying to think, okay, I've got 3 groups, right? I need 7 people in here, then 8, then 15. How do I do it? You know, and then let's get all jumbled. It's really straightforward if you think about it like this. You basically go, well, I have 30 students to start with. I'm going to choose 7. So from 30 people, choose 7, right? And then you go, well, this is the same case, right? I need to choose 8 now. So I've already chosen 7. So from 23 people, right? 30 minus 7, I'm going to choose 8. And then, of course, once I've chosen 8 from 23, from the 15 remaining, choose another 15. No order, right? No, and that's it. That's why it's worth 1 mark, right? So when you have this sort of sequential selection, right? Sequential selecting of groups, you basically just take the total minus the first group you select to start with the second group and select that and sort of keep dialing down until you get to until you selected all cases, right? And if you punch in the calculator, look, I mean, this is a big number, but I think now I just want to show you algebraically because I think the outcomes for this is actually quite nice. So I'm going to express the answer like this, right? So just to show you that this one here, now the combinatoric expansion for this is top factorial, bottom factorial, top minus bottom factorial, right? Is how I always say to my students. This guy here, I just want to show you the nice answer at the end, right? Top factorial, bottom factorial, top minus bottom factorial, and this one here, top factorial, bottom factorial, top minus bottom factorial, right? But look at this, right? It's quite nice. So if I multiply these, right, then you can see that 23 goes away, 15 goes away, this guy is 1. So your final answer is actually 30 factorial all over 7 factorial, 8 factorial, 15 factorial. Which sort of makes sense because I guess the equivalent here is that you're arranging 30 people, but with 7, 8, 15 repeats, right? That's another way to see it if you wanted to go down that path. But I like this combinatoric expression, so combinations thinking here, because it helps later on when we're starting to think when the questions are combine combinations and permutations, so selecting and arranging, right? All right, let's do another one of these similar concept, right? But in another HSC 4-unit context, right? Check this out. 2001 4-unit. So in this first question is very similar. In fact, it's exactly identical. From a class of 22 students, subdivided into 4, 5, 6, 7, how many ways can it be done, right? The 20 students, 4, 5, 6, 7. How many ways, right? So exactly the same as before. Now, the next one there is just puts a bit of spin. Yeah, ignore the pun, please. 4 groups, 22 students arranged in a circular table, right? How many ways can they be seated? Beautiful, right? The classic sort of circular question, but we've already placed them into groups, right? So, part 1. Now, using the theory that we did before, right? We can see that this is going to be 22, choose, let's say 4 people first. And then I know what's that, 18, choose 5, and then 13, choose 6, and then 7, choose 7. Algebraically, all the combinatorics, all the combination terms, factorials and stuff sort of simplifies to 22 factorial 4, 5, 6, 7. Right? Nice. Nice. That's part 1, right? Same as what we did before. We're just selecting, plotting 4 here, 5 here, 6 here, 7 here, right? Easy. Now, the next one. It's quite cool. So for the 4 groups chosen, they're arranged into a circular table. So for the circular table, you know, we sort of have like groups, first group, second group, third, and fourth. In the fourth one, first one, there's 4 people there, 5 people, 6, 7, right? So obviously the way we're going to do this exactly like we do with the circular arrangement, right? We'll lock one down so that the repetitions don't occur, right? Lock one down. Yeah, and then you go, well, within this group, there's 4 factorial ways of arranging them, 5 factorial, 6 factorial, 7 factorial, right? And then the groups, it doesn't say that the groups have to be in any order. So, you know, once you lock that down, there are 1, 2, 3 factorial ways of arranging the other 3 groups, right? So your answer is quite simply, well, 3 times 4, 5, 6, 7 factorial, right? So a little bit of a spin, right, on your usual circular table arrangement question. I thought I'd go there. Quite a nice question that sort of falls, used to fall into the 4-unit sort of camp of questions, but like I said, you know, that wall has been sort of pulled down since the new syllabus is there, so who knows? So always best to be prepared and sort of, yeah, we'll look at 4-unit questions as well. Let's move on. So in this question now, this is a classic, right? There are so many times I've seen this question asked over and over again now, repeated, and it will continue to be done so. So in this question, it says, this is one, sorry, and just to be clear, this is the start of questions where you combine combinations and permutations. It's just to be clear, the way I'm going to do this, so many ways to do this, by the way, not one, but the way I always teach my classes are, you always go for the select and then arrange. Select and arrange if you have to do multiple ones. So we'll get this right. Let's read the question. In how many ways can 11 people be seated on 2 circular tables that can accommodate 6 people and 5 people, right? So I've got 2 tables. Table 6, table 5. So from the 11 people, what I'm going to do conceptually is I'm going to, from the 11, choose 6 to arrange. And then from the remaining, choose 5 to arrange, right? So I'm always going to split my answer into, from 11 people, choose 6 people, right? So just be clear, this step here is to select, right? And then this step here is to arrange, right? Select, arrange. Theoretically, you can combine that with a permutations expression. I like to split because then conceptually you can see what you're trying to do now. How do you arrange? Well, once I've chosen the 6, right? 1, 2, 3, 4, 5, 6. Remember, it's just like arranging 6 people. So I'll lock one down and that's 5 factorial, right? So select arrange. Now for this one, same thing, right? Once I've selected from 11, choose 6, I've got 5 people left to choose 5, and then 1, 2, 3, 4, 5, lock one down, 4 factorial. So just to be clear, that step there is select and arrange. And because they're part of the same case, there's a times in between them. So multiplicative all the way. And I think if you punch it in the calculator, 1,330,560. Yeah, I like this concept of select and arrange because for the next question, right, so common now. Used to be sort of asked only in harder 3-unit and mainly 4-unit tests, but now so common, right? So common. Let's see. Classic. So I can, give you some questions for Sydney girls love asking this, right? James Roos has a few of these. It's everywhere now. Guys, this question is really easy. If from the 7 letters they give you, if I was arranging words with 7 letters, easy. You just go 7 factorial divided by repeats, right? But the trend for these questions is they give you 7 letters and they ask you to make words that are less, right? That require less letters. So then you gotta pick from the 7, pick the letters that you want and then arrange. And what makes it difficult is the arrangements. Sorry, it's the repeats, right? Because you gotta, when you choose from the 7, you choose a 5 in this case, right? 5 letters. You got to worry about the fact that some of the repeats might mess you up. That's where the cases come in. So let's see. From the letters of mammoth. Now, just to be clear, from the word of mammoth, there are 3 M's and 1, 2, 3, 4 other letters, right? 7 letters altogether. And I'm making arrangements of 5. Guys, let's consider the cases. And with these cases, the way I always teach my class is, once again, we select and then arrange, right? So let's see. Case number 1. Yeah. Now with 3 M's, let's choose a case where 3 M's are selected in my case, right? So I know if I'm selecting it, I know the selection is already 1 times 1 times 1 because all 3 M's are there. And then from the 4 other letters, choose 2. Now, just to be clear, this step here is always select. And then I'm going to arrange. Now, once I've chosen the 3 M's and the 2 other letters, to arrange them, I know there's 5 factorial, but because there's 3 M's and the repeats, I've got to divide by 3 factorial, right? This step here is arrange, right? That is case number 1, or multiplicative because it's case within the same case. Let's consider the second case, right? So obviously the cases are differentiated by the number of repeats, right? Because what it does is it changes the arrangement because the number of repeats is on the denominator, but it also changes the number of M's I select and the number of other letters I have, right? So let's go case number 2. 2 M's. So 1 M there, 1 M there, and then from the 4 other letters, I'm going to choose 3, right? To make 5 letters all up. And because there's only 2 M's, when I arrange, it'll be 5 factorial, 2 factorial, right? There's only 2 M's there. Yeah, if you punch this in your calculator step by step, that's 120, that's 240, right? And then case number 3. Let's see, 1 M. Yeah, where you go 1 M there. And then from the 4 other letters, choose 4. Guys, in this case, there are no repeats, right? Which gives me, I think on the calculator, another 120. Yeah, now we don't need to consider a case where there's no M's because I can't make 5 letters, right? I can have 4 other letters. So each of the 5-letter words has to have at least one M, right? But there you go. So within these cases, if I add them, what's that, 2 foot 480? That's how I do it. Does that make sense? So in each of these, right, select, arrange. I like that. Now, some students, I mean, you can go, for the last case, for example, you can go like 5P4, because that basically selects. Permutations by definition is a select and arrange formula. It gets a bit complicated then when you basically do it above. So I guess I'm not a fan of using the P notation or the P function on your calculator. I rather select with combinatorics and then arrange using factorials. Yeah, guys, how's that? I've got one more question prepared from James Ruse. It's not that hard, or it's a little bit hard. It's a bit more intense, but we'll see how we go, right? See how we go. Now, the question reads, 12 cards are drawn from a regular deck. So this is from 2020, by the way. 12 cards are selected or drawn from a regular deck of 52 playing cards, which includes 4 kings and 4 queens. Okay, cool. It is known that of the 12 selected, exactly 2 are kings, right? It is known, right? 2 are kings. What is the probability that there are more? So maybe all the blue is fact, right? Probability more queens than kings. Now, you might have noticed that if they told you it is known, right? If they say the words it is known, right, feels like conditional probability, right? It is known that of the 12, exactly 2 are kings, right? So what I'm going to do is basically now, for the formula of conditional probability, right? Yeah, the probability of A having known that B is true, right? That equals the P of A intersecting with B over the probability of B, right? We know that that's given in the reference paper, right? We know that. Now, so in this question, what is the probability that there's more queens than kings? So if I was to sort of summarize that, what they're really looking for is, can you please find the probability that the number of queens is bigger than kings, given that the number of kings equals to 2, right? That's really what they're saying. Is that right? Now, using the formula up here, right? They're basically saying king is 2 on the bottom. Now, the probability that the number of, if there's 2 kings, then that's really saying that the probability on top of queen, now let me write it out as if I knew the formula, right, is intersecting with k equals to 2. And if you translate, if the queens are bigger than kings and the kings are 2, well, what that's really saying is probability that number of queens equals to 3, right? Given that kings intersecting with 2s, where king is 2 already, plus the probability that queens is 4, knowing that I got 2 kings, right? And maybe I'll break, oh, maybe I don't want to break it. I was going to break it into 2 fractions, but what's the point? Does that make sense? So the top line basically says, I want more queens than kings. And that can occur when, if I have 2 kings, then that is when queen equals 3 and queen equals 4, right? So then it comes down to now, it doesn't say which queen, so the order of the queens don't matter, which is why we're going to use combinatorics now, combination. So on the bottom, right, hopefully it's pretty easy. Guys, there are 52 cards, right? Let me do that first, right? There are 52 cards. I want to choose 2 kings, right? So from the 4 kings, choose 2. From the 4 kings, choose 2. And then now, I don't want any more kings, right? So remove the other 2 kings. So from the 48 other cards, I want to choose another 2, right? That is a probability in it. Yeah. All right, let's do these ones. This guy. Now I want 3 queens, 2 kings. Oh, sorry, that's not true. How many cards am I? I'm 10, right? Sorry, I thought we were choosing 4, so that should be a 10, yeah? Because I'm choosing 12 cards all up, right? 12 cards all up. Cool. Now, for this pink part here, I want 3 queens, 2 kings, and what, 7 others, right? So pretty easy. So I've got 4 queens, choose 3. That's queens. I've got 4 kings, choose 2. And I don't want any more queens and kings. So from the other 48, 40, 44, from the other 44 that are non-queen or non-king, choose 7. That is this guy. I mean, that's not, you just got to work through, right? I think this question is harder to get started, but once you get started, it's actually pretty easy. So for the next one, say, from the 4 queens, choose 4 queens. From the 4 kings, choose 2. And from the 44, because I've already chosen, 6, choose another 6. Right? So this one here is out there, right? Does that make sense? So it's all to do with cases in this, right? But it's also conditional probability, right? And if you punch that in your calculator as a fraction, 53.2162. Guys, hopefully, I'm just going to leave it there, but hopefully that gave you a good sort of broad coverage of combinations and how we deal with them. I really like the questions that combine Perms and Combs, where combinations you select and permutations with factorials you arrange, right? If you like that video, please give it a like. Haven't already done so, subscribe, and I'll see you at the next lesson.